Hey everybody, welcome back to Mr. A's Geometry course. Today we are reviewing Unit 5. This video will help you if you're preparing for an assessment on anything to do with triangle measure or triangle congruency. Let's get into it. We're going to start our review off here with some triangle sum theorem problems. Our first problem here tells us that two angles in a triangle are 48 and 87 degrees. It's asking us for the measure of the third angle. So with that third angle being unknown, we can refer to it with a variable like x. And the idea here is knowing that all three angles in any triangle must add up to 180 degrees. So this would be our equation to solve for this third angle. Combining like terms here, the 48 and 87 will give me, 127, 135 degrees. And if we subtract that 135 from both sides, we will get 45 degrees for that third angle. And we're asked to classify it by its angle measures as either acute, obtuse, or right. And acute triangles will have all three angles less than 90 degrees, which is exactly what we have. 48, 87, and 45 are all less than 90 degrees. That makes this an acute triangle, right? We will carry some of that logic over to our next problem. We're asked to solve for the measure of angle E in this triangle. Again, this is just triangle sum theorem, knowing that all three angles must add up to 180 degrees. So that means the 6x from angle E plus the 3x from angle O plus the 11x from angle G must add up to equal 180 degrees. Combining like terms here, we would get 20x equal to 180, and then we divide both sides by 20 to get x equals 9. And where you need to be careful on testing, especially for triangle measures, is answering the questions that are being asked, because we're often not asked just to solve for variables, but to find angle measures. So we need to find the measure of angle E, so that 9 needs to get plugged into that 6x for angle E. So 6 times 9 will give me a measure of angle E of 56 degrees. No, 54 degrees. My apologies. Our next example, we got another triangle sum theorem. Again, we're just reviewing here, making sure that you understand this. Why don't you go ahead and pause the video here and see if you can find the value for x on your own here. Remembering all three angles in the triangle have to add up to 180. See how you do. All right, again, the key here is understanding what you're looking at and knowing the properties. This is a triangle. We're dealing with the angles of the triangle because all these values are inside of our figure, and we know the angles in a triangle must add up to 180 degrees. So the 3x minus 17 plus the 2x minus 5 plus the 42 has to equal 180. Again, that's the geometry. It's can you get to this equation? From here, we must be able to solve this with appropriate algebra skills without making any mistakes. 3x plus 2x, those combine because they're on the same side of the equal sign as 5x's. Then we have negative 17, negative 5, and positive 42. These combine to give me positive 20. Again, using all the same signs, that'd be negative 17 minus 5, and then plus 42 would give me positive 20. From here, I can get that 5x alone by subtracting 20 from both sides. I get 5x equals 160, and then I can divide both sides by 5 to get x equals 32 degrees in this example. All right, I got one more problem here that involves our triangle sum theorem. This is just a little bit more in disguise because we have multiple triangles here. We have this triangle on the right, we have this triangle on the left, and then we have this large triangle. There's several different routes that we can take to solve for these variables. I'm going to give you a triangle sum theorem, and I'm going to give you an exterior angle theorem in this problem too, because that's useful in this unit. So we're going to start off with x over here in this triangle. We know all three angles of the triangle have to add up to 180, so solving for x is just x plus 28 plus 39 equals 180. Triangle sum theorem for that triangle. Combining like terms here, we have 28 plus 39, that is going to be 67. And then we can get x by itself by subtracting that 67 from both sides, and we can determine that x would be 113 degrees. And I'm going to go ahead and add that into my figure here for visual sake. Now what we can do is solve for y one of two ways. We can do a linear pair there with y and x. They're side by side on a straight line. We need to be good at recognizing that linear pairs have to add up to 180. But again, I'm going to give you a exterior angle theorem here to introduce you to that. So y is the exterior angle on this triangle, and that has to equal the sum of those angles that are furthest away, those non-adjacent angles in there. So y has to equal 28 plus 39. Okay, and we're doing the correct algebra here. We're going to get 67 degrees for that problem, for y in this problem. Then we can do another exterior angle theorem. I'm going to show you here on this triangle. We have 113 as the exterior angle now for the z and the 64. And so we can set up this equation now that exterior angle 113 will equal the sum of these non-adjacent angles z plus 64. Then we can get z by itself by subtracting 64 from both sides. And that will give us, let's see, we'll get to 53 minus 4, it'd be 49 degrees for z in this problem. And for anyone that is struggling a little bit with the exterior angle theorem, that's not the only way we could have solved for the angles that are involved in this problem. Once we got that 113 with triangle sum theorem, we could have just used a linear pair here and just say that y plus 113 equals 180, and we would get the same 67 degrees for the y. Then we could have done the triangle sum theorem for this triangle and just say z plus 64 plus 67 equals 180, and we would get that same resulting value for z as well using that triangle sum theorem. So multiple routes we could take there. And the only reason I showed you the exterior angle theorem is because that's coming up in our next few problems. Our next few examples here are going to involve that exterior angle theorem, just a little bit more straightforward than they were in this example. So we only have one triangle here. The 113 degrees is outside the triangle, and our theorem says that must equal the sum of the non-adjacent angles. So we ignore this adjacent angle, right? And we're going to use these non-adjacent angles, the two that are furthest away. And our theorem says that 113 will equal the sum of those non-adjacent angles. So it'll equal x plus 53, right? And we do the appropriate algebra there, just subtracting 53 from both sides. We're going to get 60 degrees for x in this example. Let's see another one involving our exterior angle theorem here. This case, we have the 124 degrees as our exterior angle, and we have the x and the 3x as our non-adjacent interior angles. Still the same setup though. That exterior angle has to equal the sum of those non-adjacent angles. So 124 will equal x plus 3x. That's 4 x's. And we divide both sides here by 4, and we're going to get 31 degrees for x. We just need to be careful though, make sure we're answering the question being asked. It's asking us for the measure of angle B, so we need to plug that 31 into angle B. 3 times our x of 31, and that will give us a measure of angle B of 93 degrees in this example. Our next example is maybe our more extreme algebra version of the exterior angle theorem because we have x's everywhere. And so the reason that this example is important is because this truly tests your exterior angle theorem. In these problems before, we could have used a linear pair to find the measure of this angle inside the triangle and then just did our triangle sum theorem. So we could solve this without the exterior angle theorem. That is a much more difficult thing to do in this example because we don't have a value on this exterior angle to give us that third angle in the triangle without having a nasty little expression in there, right? So this example truly requires your understanding of the exterior angle theorem. Exterior angle is 6x minus 7, and that must equal the sum of these non-adjacent angles. So it's got to equal the sum of 2x plus 103 minus x. We don't need to worry about the parentheses here because we're adding. If we were subtracting, that'd be a different story, which is why coming up with that angle is kind of a difficult task to do here. Now we're just doing algebra to solve for x. Combining our like terms here, on the right side I have 2x minus x, that'll leave me with just 1x on the right. So I got x plus 103. Now I can move this x to the left by subtracting on both sides to give me 5x minus 7 equals 103. And then I can add 7 to both sides to get 5x equals 110. And now I can divide both sides by 5 to get x equals 22 degrees in this example. Our next example here is also using the exterior angle theorem, but maybe in a more complicated way because we don't have anything drawn in our figure. So this is a great example of how you need to know how to identify angles when they're named and how to mark information in your figure. So we're told angle SRT is congruent to angle STR. So this is angle SRT. This is angle STR. That first statement says those are congruent. I'm gonna go ahead and mark that by giving them the same amount of arcs here. Those are congruent to each other, making this an isosceles triangle, something that we'll cover, I'm sure, on future examples here in this review. We're told angle SRT is 68 degrees, so this is 68 degrees. Remember, these angles are congruent, so this angle must also be 68 degrees. And then we're told that angle STU is 4x. Angle STU, if I trace from S to T to U, give me the interior space here outside of our triangle. So this is our 4x, and we're being asked to solve for x. So exterior angle kind of in disguise here, our exterior angle theorem. We could solve for this vertex angle and then say that 4x would equal 68 plus this, and we would solve for that with our triangle sum theorem. However, there's an easier path to this, and I'll show you that on this one. We have a linear pair right there. Side by side on a straight line, those angles must add up to 180 degrees. Linear pairs are always supplementary. So 4x plus 68 equals 180, and we can do the algebra here to solve for x. Subtract 68 from both sides, we get 4x equals 112. Then we can divide both sides by 4 to get x equals, I think that would be 28 degrees for this example. Now we're starting to get into our review of specific types of triangles. We're told to solve for the variables in this equilateral. Very important to know that your diagrams, your figures don't have to have any kind of marking. Sometimes the important information is in your directions, so make sure you're thorough in reading your directions. If this is an equilateral triangle, the thing to remember is that all the angles have to be equal, meaning all the angles have to be 60 degrees. For the three angles to add up to 180 and they're all the same value, they would all have to be 60. 60 plus 60 plus 60 would give me 180 degrees. So this angle, where x is, has to equal 60. 6x equals 60, divide both sides by 6, and you find out that x is 10 degrees. This angle, where y is, has to equal 60. So 9y minus 3 must equal 60. Got to add 3 to both sides here. You get 9y equals 63. Divide both sides by 9. Y equals 7 degrees in this example. It's important to remember that the angles are always inside your triangle. Sometimes students will take things that are outside the triangle and try to set them equal to 60 or 180 degrees. Remember, only in the equilateral at the angles inside are going to be 60 degrees. Next up, we have an isosceles problem to review here. We know this is isosceles because we see two sides with the same amount of dashes. That gives me two congruent sides. We call those isosceles triangles. We're told angle B is 32 degrees. I'm going to go ahead and mark that in my figure, as you should always do in your own problems. We have to find the measure of angle A. I'm going to assign a variable to angle A because I have none already given in this problem. I can just call this x. And the key to this is really understanding the parts of our isosceles triangle to solve for angle A. Those congruent sides we call legs. So this is a leg, this is a leg. This third side is called the base. And that important thing to remember is the two angles that touch the base are our base angles, and those are the two angles in the isosceles that are always congruent. So just like we have two congruent sides, we have two congruent angles. Those are always the base angles. So if angle A and angle C are the same, and angle A is x, then angle C is also x. And now I can solve for these variables with a triangle sum theorem. These three angles have to add up to 180 degrees. So x plus 32 equals 180. Those x's combine to give me 2x. I can get 2x alone now by subtracting 32 from both sides. I'm gonna get 2x equals 148. Then I can divide both sides by 2 to get 74 degrees for x in this example. Here we have another isosceles triangle, and we have to find the side lengths of our triangle now. So these sides now outside the triangle have nothing to do with 180 degrees. Maybe you're confused about the 61s. The 61s are there just to tell us what type of triangle this is, because the directions don't say. But the angles tell me there's two congruent angles. This must be an isosceles triangle because it has two congruent angles. This side must be the base because that's the side my two congruent angles are touching, which means these sides are my legs and the legs are the two congruent sides of the isosceles triangle. So to solve for x here, we are setting these equal to each other. 5x minus 21 has to equal x plus 3. And we're doing algebra here to solve. I can move this x by subtracting x from both sides. I'll get 4x minus 21 equals 3. I can get 4x alone by adding 21 to both sides. So that gives me 4x equals 24. Then I can divide both sides by 4 to get x equals 6. Now we haven't answered the question yet. We have to solve for the length of the labeled sides. So now this 6 just needs to be plugged in. It doesn't matter which side we plug it into. It's probably best practice to plug it into both just to confirm that your answer is correct. I'm just going to stay organized here and say side equals x plus 3, and then substitute in my 6 for that x, and I get a side length of 9 units. And if I plug that into the 5x minus 21, I would get the same result. The side lengths here in this triangle are 9 units long. Got another great question here, reviewing specific types of triangles. The directions say it's equilateral. Our dashes tell me it's equilateral. All the sides have the same amount of dashes. That means all the sides are congruent to each other. The challenge here is knowing which variable you have to solve for first and remembering that these are sides, not angles. These have nothing to do with 60 degrees or 180 degrees. I have to solve for x first because I can't set this y equal to another expression that has an x in it. I can't have those two unknown variables in the same equation. However, I do know these sides need to be congruent, so I can set 6x minus 7 equal to x plus 8, and I can solve that. I can subtract x from both sides here. That'll give me 5x minus 7 equals 8. I can add 7 to both sides. That'll give me 5x equals 15. And then I can divide both sides by 5 to get x equals 3. Now solving for y, some people get a little lost here after they solve for x. We have not found the length of the sides yet. That needs to be our next step here. We need to plug this 3 in to a side length. The easy one will be that x plus 8 on the bottom. So I'm just going to substitute my 3 for the x, and I can determine that that side has to be 11 units long. If I plugged it into the 6x minus 7, I would also get 11. And because this is an equilateral, this side must also equal 11. Therefore, I can solve for y with this equation. 3y minus 7 must equal 11. And I can add 7 to both sides to get 3y equals 18. And then I can divide both sides by 3 to get y equals 6 in this example. The rest of our study guide here is going to go over congruent triangles. And our first example here is really just a review of congruency statements and making sure that you understand how they are ordered. So assuming these triangles are congruent, because there is not technically enough information to say that they are, but assuming that they're congruent, we could write a triangle statement or a congruency statement by matching corresponding congruent parts. For example, if I name this triangle on the left triangle BAC, just a random name, I can name the other triangle in a way where the congruent parts match. For example, angle B was the first letter in this name, and that's congruent to angle Q, so Q will have to be the first letter in the name for the other triangle. Then side AB is congruent to side QP, so those letters Q and P need to be the first two letters for my triangle because A and B were the first two letters for this one. So QP has to be the first two, leaving R as the default last letter for that congruency statement. Our next example has this very common situation where we have triangles that are not currently congruent. We're being asked to find the missing piece of information to make them congruent by a specific theorem, so by the side angle side theorem. First, we want to evaluate what we already have, side UV congruent to side VK, that is a pair of sides, that's an S. We also have vertical angles. Remember, we are responsible for marking these vertical to each other, so that's not missing information. That's expected to be known. That's a pair of congruent angles. So what's missing for side angle side is that other pair of congruent sides. We need to figure out which sides would have to be congruent. The key is remembering that for side angle side, the angle needs to be the included angle of our two sides. So the sides with marks needs to put that angle mark in between them. For this triangle, that would have to be side WV here. For this triangle, that would have to be side VM, right? So WV and VM, that would be this option D here in this example. In example 15, we had to determine if triangles are congruent. What I like about this example is that there's nothing marked on the triangle to start. We have to read directions and apply that given information to our figure. For example, it says if angle B is congruent to angle E, so that'd be this angle congruent to this one, and angle A is congruent to angle D, so this angle congruent to this one, it says, is there enough information to prove these triangles are congruent to each other? Remember, we're responsible for vertical angles, so we're responsible for knowing that angle BCA is congruent to angle DCE. And what we have given to us is 3 pairs of angles. And we need to obviously have all of our congruency theorems memorized. We have no theorem called angle, angle, angle. This is not proving triangle congruency, therefore there is not enough information to prove it. That is us justifying our answer. Angle, angle, angle does not give us congruency. If there were a congruent side anywhere on here, that would give us congruency, but we don't have that, so they are not congruent. We got a 3 for 1 here in example 16. We have triangles 1 and 2 that we need to prove congruent by any postulates necessary. For 1 and 2 on our first example, we are responsible for marking the shared side. In addition, something we haven't covered a lot is we're responsible for marking the measure of this angle here. This is a straight line, which will have 180 degrees on it. If this angle is 90, this angle next to it must also be 90. And that gives me angle, side, angle congruency between these triangles. In figure 2, we again have vertical angles here that we are responsible for marking. That gives us side, angle, side congruency for both triangles, side, angle, side. For our last example, we have that scenario again with the right angles. We know this angle needs to also be 90 degrees. We have the shared side. It says 2 sides and an angle, but the angles here, these right angles, are not the included angles of our sides. This instead gives us hypotenuse leg congruency theorem for these 2 triangles. Again, very important that you know how to identify your congruency theorems. If need be, you can go back and look at my triangle congruency video lesson for that information. 17 is a great example of why knowing your symbols for geometry is extremely important. This geometry notation is a big part of this course. This says segment FH is perpendicular to segment GI. And now you also need to know our vocabulary. We gotta know what perpendicular means. That means those segments are going to intersect at right angles. So FH right here, GI right here, they intersect at I. So there needs to be right angles there at I. Right? We also have 2 triangles that are sharing side GI. We're responsible for marking that as a congruent side for both. And the question is there enough information to prove the triangles are congruent, specifically by the side angle side theorem? For both triangles, we do have 2 sides, and the included angles happen to be our right angles. All right angles are 90 degrees, therefore they're congruent. So we can say, yes, these triangles are congruent by the side angle side theorem. And again, I showed all the appropriate markings here on my figure to prove that. Example 18 has given us a little freedom to come up with our own congruency theorems for each of these figures. By the way, postulate and theorem kind of meaning the same thing here, are shortcuts to proving that triangles are congruent. As is in this first example, these triangles are not congruent to each other, But if we are marking our shared side df, that does give us two different theorems that can apply here. So the roadblock in this example is some students will immediately look at it and say angle, angle, angle is not a congruency theorem, and therefore those triangles are not congruent. However, the shared side there does give us a theorem. So technically we added that df is congruent to df. That is a reflexive property, and that can give us either angle, angle, side congruency, or we could say angle, side, angle congruency between these. I'll go ahead and say angle, side, angle for this example. And again, the key here is that we're not using that theorem again as we go to our next one. So here, these triangles are not touching. Therefore, there is no congruency theorem that proves them congruent right now. We're going to have to add something to make them congruent. We just don't want to use angle, side, angle again, right? So we're going to use something different. So what I have a pair of sides. I have a pair of angles. Okay, what sticks out to me is the side angle side theorem. I can make that happen by making this angle, those right angles, the included angle of two marked sides. For this left triangle, that would have to be side SU. For the right triangle, that would have to be side FH. So what I added was side SU congruent to side FH, and that gave me congruent triangles by the side angle side theorem. Looking at our last pair of triangles, again, I've already used angle, side, angle, and side, angle, side. I need to come up now with a different theorem to apply here. And I'm going to review hypotenuse leg with you guys, because sometimes students struggle with that theorem. For hypotenuse leg, we need right triangles, which we have here. We need the hypotenuse, the longest side, the side that doesn't touch the right angle, to be congruent. For the triangle on the left, that would be side NM. For the triangle on the right, that would be side XZ. And marking those gives me right triangles with hypotenuses that are congruent and another pair of sides, legs that are congruent. That makes these congruent by the hypotenuse leg theorem. So I added NM congruent to XZ, and that gave me congruent triangles by the hypotenuse leg theorem. In example 19, we have another one where our figure does not have any markings on it already. We have to take this given information, interpret it, and mark those congruent pieces on our figure. So angle ABD is congruent to angle CBD. ABD is this angle, CBD is this angle. It says they're congruent, so I'm going to mark them congruent to each other. Then it says that AB and BC both equal 11. So that means they're congruent if they're the same length. So side AB congruent to side BC. We are also then responsible for marking the shared side between these triangles, which is side BD. Then we're asked, is that enough information to prove these triangles are congruent? And it absolutely is. For both triangles, we have two sides and the included angle. These are congruent by the side angle side theorem. We have another similar example here in question 20. It says somebody's building a window. In this diagram, when remodeling the studio, we see that AB and CB both measure 9 feet. AB, CB, 9 feet. Underneath here, it says if angle BCD is congruent to angle BAD, is there enough to prove? So BCD is this angle, BAD is this angle. We would be responsible for marking those since it tells us that those are congruent. We're responsible for marking the shared side BD. And it's asking us if this is enough to prove these triangles are congruent to each other. And this is not enough, because yes, we have two sides and an angle, but the angle is not the included angle of my two sides. Therefore, there is not enough information to prove these are congruent to each other. If you're ever concerned about your theorems, you can't remember what they visually look like, then something that I suggest is writing out all your theorems. So you need to memorize all of them. If you write them all down, you can just test your criteria. For example, I know these triangles are not congruent by side, side, side because the third sides are not marked congruent, so that doesn't fit, right? I know they're not congruent by hypotenuse leg because I need right triangles for that, and I don't have that, and we can't assume that those are right angles because there's no proof of it. So they're not congruent by hypotenuse leg. It can't be angle, angle, side, or angle, side, angle because I don't have two angles in each triangle. Then it can't be side, angle, side for the reasons we said earlier. Those angles would have to be the included angles here at B for side, angle, side. So it's not any of our 5 theorems, and these triangles are not congruent to each other. The last thing that we're going to review here is how to solve for angles or side lengths using congruency statements. We have to solve for x and y here. We're given a very clear congruency statement between our triangles that tells us all the matching corresponding pieces here. For example, we see x is at an angle. It's at angle A. Angle A is the first letter in the name of triangle ABC, and our congruency statement, the first letter over here is D. So these angles correspond on our congruent triangles, therefore they must be congruent. So if angle D is 60 degrees, then angle A must also be 60 degrees. So x is 60 degrees. We do the same exact logic to solve for y. This time though, y is on a side, right? It's on side CE. That's my last two letters here. That'll correspond with side BC, the last two letters here, which is 42 units long. So because the triangles are congruent, these corresponding parts must also be congruent, and therefore y is 42, right? The complex version of this is not giving you any kind of figure at all, just giving you a congruency statement like we have here in our last example. So triangle JKL is congruent to triangle TUV. It's asking us to solve for three variables here, x, y, and z. So let's start with x. X is on side UV, which says in our directions equals 2x plus 5. In our congruency statement, UV is the last two letters. That corresponds with my last two letters here, KL, and side KL is 28 units long. So to solve for x, I just need to know these corresponding pieces must be equal since the triangles are congruent to each other. So 2x plus 5 has to equal 28, and then we can solve for x from that equation. Subtracting 5 from both sides will give me 2x equals 23. Then I can divide both sides by 2 to get x equals 11.5 in this problem. And then we can move on from there to find all of our other variables in this problem. So y is on side TV. TV is the first and last letter. In our congruency statement, that'll match first and last JL from our other triangle, and side JL is 15 units long. Therefore, 3y minus 3 must equal 15. We can add 3 to both sides to get 3y equals 18. Divide both sides by 3, and y equals 6. And then one more time, we can repeat this to solve for z. Z is on side TU. TU is the first two letters in our congruency statement that corresponds with JK, the first two letters over here, which is 21 units long. So 7z equals 21. We can divide both sides by 7, and z equals 3. So again, the key is that congruency statement tells you all the matching pieces. Angle J is congruent to angle T, K is congruent to U, L is congruent to V, side JK is congruent to side TU, and so on. Guys, this wraps up our review of Unit 5. You need to know how to find triangle angles and sides with our theorems. We need to be able to prove that triangles are congruent to each other with our congruency theorems. We'll see you on the next unit. Bye, guys.